Welcome to This Explainer. We rarely think about it, but right now we are all sitting at the bottom of a massive swirling ocean of gas. Our atmosphere is this incredibly dynamic system, literally a blanket keeping us alive, but it's also remarkably fragile. Today, we're going to untangle some of the most complex, even twisted questions about how our atmosphere works. We'll break down the hard science behind things like temperature and rainfall, and then look at the macro-level crises caused when human behavior throws these natural engines totally out of whack. Here is our roadmap for today. 1. The global warming crisis. 2. Protecting the ozone layer. 3. Weather versus climate. 4. Factors influencing temperature. And 5. Pressure, wind, and moisture. Let's jump right into section 1, the global warming crisis. Let's start with a really fascinating thought experiment. Imagine if we could just snap our fingers and instantly wipe out all greenhouse gases tomorrow. Sounds like a win, right? Actually, scratch that, it would be a total disaster. We would freeze. The truth is, the greenhouse effect is absolutely essential for our survival. During the day, the sun heats the Earth. At night, the Earth cools down by releasing that heat back out. Greenhouse gases naturally trap some of that outgoing heat so it doesn't escape into deep space. The crisis isn't the greenhouse effect itself. It's that a rising, unnatural concentration of these gases is throwing off a very delicate balance, and it's trapping way too much heat. So what's actually altering this balance system? Well, our sources point to 5 main culprits. First, burning fossil fuels like coal and petroleum releases massive amounts of carbon dioxide. Second, booming industrial growth pumps out harmful oxides of nitrogen and sulfur. Third, rapid deforestation and mining are wiping out our forests. Those forests act as vital carbon sinks, so without them, more carbon just sits in the air. Fourth, and this is a big one, the massive scale of raising farm animals like goats and sheep produces enormous amounts of methane gas. And finally, using artificial nitrogen fertilizers for crops directly spikes nitrogen oxide levels. When you see vast, sprawling mining operations completely tearing through essential forests just to access resources, the sheer scale of the human footprint really hits you. And then you have those massive factory stacks pumping thick, heavy smoke into the sky day in and day out. These aren't just isolated events. This is a relentless industrial engine, fundamentally changing the chemical composition of the very air we breathe. And the physical reality of all that trapped heat? We're seeing massive, objective melting of permanent ice sheets in the Arctic and Antarctic. It's not just a symbol. It is a direct, physical reaction. As global temperatures creep up, these massive glaciers fracture and break apart. All that stored ice converts to liquid water, significantly raising ocean volumes and putting coastal areas under severe threat. What's absolutely wild here is how interconnected all these impacts are. A temperature increase doesn't just mean a few warmer summer days, it's a massive domino effect. Higher temperatures spike evaporation rates, which dries up soil and ruins crops, leading to severe droughts. But it gets darker. Intense heat waves actually help spread vector-borne diseases like malaria and dengue fever. Meanwhile, those rising sea levels we just talked about, they're threatening to submerge entire islands, creating climate refugees and destroying critical marine ecosystems like coral reefs. All right, moving on to section 2, protecting the ozone layer. To really wrap our heads around ozone depletion, we have to look at the microscopic chemistry. It's almost like a microscopic demolition derby up there. When an ozone-depleting substance, like a CFC from an old aerosol can, drifts up into the stratosphere, UV radiation smashes into it and breaks a single chlorine atom off. That highly reactive free chlorine atom acts like a wrecking ball. It crashes into an ozone molecule, literally steals one of its oxygen atoms, and rips the ozone apart. And the most terrifying twist, the resulting chemical reaction eventually frees up that chlorine atom to go destroy another ozone molecule over and over again. But hey, we actually have some incredible news on this front. Thanks to the Montreal Protocol of 1987, which globally banned many CFCs, we are seeing real recovery. In fact, due to those restrictions and specific wind patterns called a polar vortex, the massive polar ozone hole over the Antarctic visibly closed up over just a single month in spring of 2020. It is hard proof that when humanity actually cooperates to cut harmful emissions, the atmosphere has a remarkable capacity to heal itself. Okay, section 3, weather versus climate. We hear the phrase climate change constantly, right? But if you walk outside and get caught in a sudden downpour on a Tuesday afternoon, is that the climate? People mix this up all the time, so let's clear up exactly what it is we are changing. Think of weather as your highly dynamic, day-to-day local experience. It changes by the hour. A sunny morning can easily turn into a stormy afternoon in your specific town. Climate, on the other hand, is the big picture. It is the stable, permanent average of those conditions calculated over a vast region, like an entire country, and requires at least 30 to 35 years of data. That's why we can say the Sahara Desert has a hot, dry climate, even if they happen to experience one random, unexpectedly chilly day. Let's dive into Section 4, Factors Influencing Temperature. So, what actually controls that climate? It's not just about how close you are to the equator, it's a massive, complex puzzle. Altitude matters because air gets thinner and colder the higher you go. Distance from the sea is huge. Coasts have moderate temps, while inland areas get extreme heat and cold. Even ocean currents play a massive role. The warm North Atlantic drift famously keeps the coast of Norway ice-free in the winter, despite being so far north. Add in prevailing winds and local forest cover, and you start to see why London needs wool coats while Singapore is strictly light cotton. And driving the global wind patterns within all of this is the Coriolis force. Because the Earth is constantly spinning on its axis, winds do not just blow in a straight, predictable line from high to low pressure. Instead, they twist. In the northern hemisphere, they curve to the right. In the southern hemisphere, they curve to their left. This invisible mechanical force literally twists our global weather systems into shape. Which brings us to a rather twisted question straight from our source material's Curiosity Corner. What if the Earth's rotation spun those crucial monsoon winds the opposite way? The moist winds entering India during June and July are entirely guided by that rightward deflection in the northern hemisphere. If they suddenly deflected left instead, they might completely bypass the Indian subcontinent. It would utterly devastate the rainfall patterns that billions of people rely on for farming and survival. Just a slight twist in physics, and the world looks entirely different. Let's wrap up the mechanics with Section 5, Pressure, Wind, and Moisture. To really understand rainfall, we have to separate two concepts that are constantly confused: absolute humidity and relative humidity. Think of the air like a sponge, right? Absolute humidity is the raw physical amount of water in the sponge. Relative humidity is a percentage telling you how close that sponge is to being totally full. Now, warm air can hold way more water than cold air. So if the air currently holds 25 grams of water, but its absolute maximum capacity at that specific temperature is 50 grams, your relative humidity is 50%. Once that relative humidity hits 100%, the air is saturated and boom, precipitation occurs. But how it rains depends on the geography. Convectional rainfall is basic. The ground gets hot, warm air rises, expands, cools, and rains. Orographic rainfall is structural. Moist wind hits a giant physical barrier, like a mountain range, gets shoved up, cools, and drops its rain. And finally, cyclonic rainfall happens when two massive air systems, one warm, one cold, crash into each other, creating turbulence and forcing the warmer air up to cool and condense. As we wrap up this explainer, I want to leave you with one final thought. Understanding how this incredible, fragile atmospheric blanket works is just step one. The real question is, how can you balance your own impact on this system? Our sources challenge us to create a climate change scoreboard. Do you leave lights on? Do you recycle? It sounds small, but when you multiply those actions by billions of people, it dictates exactly how many greenhouse gases are pumping into the air and altering the very weather mechanics we just learned about. The climate isn't just something happening out there. It's something we interact with every single day. So what's one habit you're going to change tomorrow? Thanks so much for joining me on this deep dive.